Hello everybody, welcome to the first of what I'm hoping will be hopefully a lot and the start of A-level papers I'm going to make for Edexcel's maths course, starting with a mechanics paper back in 14th of June 2019. I've started with a mechanics paper because as a general rule I do find students struggle quite a lot with mechanics questions, especially the very brutal force diagram questions. And to be fair, if I don't do these questions myself regularly, or if I don't teach them for 1 or 2 years, I can get rusty as well. They take lots of practice and just need to be kept fresh in your head. So let's have a look at the questions. I'll talk some through in more than one method. Sometimes I'll just be one method I'm showing just for a balance between efficiency and also not boring you to death. So let's have a look at question 1 anyway, which is about vectors. So it's all relative to a fixed origin 0, or capital O. So at time t seconds, where t is equal to or greater than 0, a particle, capital P, moves so that its velocity, v meters per second, is given by this vector equation in terms of I and j components. We're told when t is 0, the position vector of p is minus 20i plus 20j meters, and we need to find the acceleration of p when t equals 4. So let's just start with information we're given. So we've been nicely told what the velocity is. So the velocity is this in vector form. We now need to remember how to find the acceleration from the velocity. We essentially just differentiate v, and so the acceleration vector a will be dv by dt. We just differentiate each component individually with respect to t. So 6ti will become 6i, and minus 5t to the 3 over 2. The 3 over 2 will come to the front and multiply with 5, so I get minus 15 over 2. And the power of t will drop by 1, so now becomes t to the 1/2 lots of j. We want to find the acceleration when t is 4, so therefore dv by dt, which is the acceleration when t equals 4, this is just notation saying the acceleration when the time is 4, we just sub in t being 4. So 6i is independent of t, so that just stays as 6i. Then we're going to have minus 15 over 2 t, which we now sub as 4, to power 1/2 j. Now using your calculator or otherwise, obviously we're going to have 6i, that's going to stay. 4 to the half is the square root of 4, which is 2. Those 2's cancel, so I'm just going to have minus 15j. So the velocity is, sorry, the acceleration is 6i minus 15j lots of meters per second squared. So we've done part A. Part B, we now need to find the position vector of p when t equals 4. So to find the position vector from v, well, when we differentiate v, we found a, we go the other way if we're trying to find a position vector. So to find displacement, or the position vector essentially, we integrate v. So r, we can find by integrating v with respect to t. And so if we do that, we're integrating 6ti minus 5t to the 3 over 2 j, all with respect to time. So 6ti, that's going to become 3t squared I. This here, the power of t will increase from 3 over 2 to 5 over 2, and then I divide the minus 5 by that new power 5 over 2. So minus 5 divided by 5 over 2, that's actually going to give us exactly 2, so that's going to give us minus 2 lots t to the 5 over 2 now, j. Plus, of course, a constant of integration, but because we're in vector notation, the way I teach it, I tend to just put a c vector here. Some people say it's just r0, but I'll explain. Just to link it back to normal integration, I now have to think about how we find the constant. We have to substitute in a known point. So we're told the position vector when time is 0. So what I can sub in here is now when t is 0, r, which I suppose you can say is r0, is minus 20i plus 20j. So I've just got this essentially from this bit of information within the question. So now I can just substitute this in. So therefore, when time is 0, we've got minus 20i plus 20j. That's going to annoy me because that looks like it's not separated. There we go. So minus 20i plus 20j, in other words, r0, that must equal this thing here when t is 0. So 3 times 0 squared I, the I component vanishes. Similarly, with the j component, we just get left with c. So in piecing this together, now we know what c is, we can simplify and say what r is in terms of this and now c. So therefore, r is going to be 3t squared, this component of I, but I got minus 20 here. So if I piece this together, that gives me 3t squared minus 20 lots of I. And in a similar fashion, if I can just group together the j components, got minus 2t 5/2 lots here, then plus 20 there. So I'm going to start with plus 20. So 20 minus 2t to the 5/2 lots of j. So we're almost done. But what I'm actually trying to find, it's easy to actually lose sight of what you're trying to find sometimes with these questions, is I'm trying to find the position vector of p when t equals 4. So now I just sub in t being equal to 4, essentially. So all I need to do now is sub t equals 4. And if I do that, I then get what r is when t equals 4. So r when t equals 4. So just sub in this. So 3t squared minus 20 is going to be 3 times 4 squared, 48 minus 20. We're going to have 28i. And this here you can do using indices, or if you want to just let the calculator do the hard work, you absolutely can. It doesn't really make any odds, to be honest. So using the calculator, we can do it this way if you'd like, just to be a bit lazy. But it's one of the perks of doing A-level maths. One of the perks is you can actually use your calculator to do some legwork. So 2 lots of 4 to the power of 5/2. So that gives minus 44 rather. So the j component is minus 44. So we can polish off there, and we've done part B as well. So the position vector when t is 4 is 28i minus 44j meters. Let's now have a look at question 2. So question 2, we've got a particle p moving with constant acceleration 2i minus 3j meters per second squared. At time t equals 0, we're told the particle is at the point capital A and is moving with velocity minus I plus 4j meters per second. At time t equals capital T, p is moving in the direction of vector 3i minus 4j. We have to find the value of t. So here it's a bit hard to know even where to start. What I would suggest though here is looking at this final line here. P is moving in the direction of vector 3i minus 4j. What this is actually saying to us is that at t equals t, the velocity is in this direction. So essentially, at t equals capital T, v is parallel to that vector. It's going in that direction. So it's parallel to 3i minus 4j. So, in other words, the velocity at time t, if the velocity is going in a direction parallel to 3i minus 4j, then velocity will be some scalar multiple of 3i minus 4j. So I'm going to make a note of this to return to later. So due to that piece of information, we can deduce this. So it's going to relate this question in terms of v. So this is a bit of a clue here, and as well as this, constant acceleration, so we can use 𝑠𝑢 that if needed in a vector space. First of all though, if we just look at this constant acceleration a, then we can remember that we can find v by integrating a with respect to time. So v is going to be the integral of a with respect to time. So that's going to be the integral of 2i minus 3j with respect to time. Now, neither of these components have time within them, so essentially it's just constants. So this is going to become 2ti, 3j integrated with respect to t will become 3tj. Then, of course, plus some vector constant, which I need to find. So then we need to just sub in something else we know. So we're told when time is 0, we're told actually, yes, when time is 0, the velocity is minus I plus 4j. So we can sub this information in. So when t is 0, the velocity is minus I plus 4j. So if we sub this in, so essentially set everything where time is 0, we get that c, because that cancels to 0, when time is 0 that cancels, we just get c must equal minus I plus 4j. Because if you sub t equals 0, the only thing that will be left will be c, which has to be this. So therefore, we've got a complete expression now for the velocity of this particle. So therefore v, if we combine the I components, I've got 2t minus 1i, so that's going to be 2t minus 1 lot of I. And then the j components, I've got a positive 4j here minus a 3tj there. So the j components can factorize out the 4 and the minus 3t, then put j. So that's quite useful, and we can now use this to do the next part of part A. So we now need to find the value of t itself. So we now need to think about what we said before, which is this: at time t equals t, v is parallel to that vector. And so the velocity at time t is some k multiplied by 3i minus 4j. So now let's think about when t equals t. If I expand this out, the velocity at time t will be 3ki minus 4kj. So 3ki minus 4kj. So just to remind us, I'm getting this information from the yellow. So that expression there must equal this expression here, subbing little t for capital T. And so that's going to be 2t minus 1 lots of I plus 4 minus 3t lots of j. I can now equate these components. So because one is equal to the other, I can deduce therefore that the 3k, the component of I here, must be equal to 2t minus 1. So I can say 3k equals 2t minus 1. And in addition to that, I can also say that this minus 4k here, the component of j, must be the same as this 4 minus 3t. So therefore minus 4k equals 4 minus 3t. Now these, as you can see, are simultaneous equations. So if I were to try and eliminate k, I'm not really interested in k, I'm trying to find t here. So I could eliminate k. I could use my calculator for this, of course, for class whiz. a simultaneous equation solver, but just showing you algebraically. To eliminate k, I could get the coefficients of k to be equal in magnitude. So if I multiply the top equation by 4 to get 12k's, multiply the bottom one by 3 to get minus 12k, this would then give me 12k equals 8t minus 4, and at the bottom, minus 12k equals, times this by 3 now, so I get 12 minus 90. And I can combine these together by adding them. The k's will cancel, 12k plus minus 12k disappears, so I get 0. 8t minus 90 is minus a t, and then 12 plus minus 4, or minus 4 plus 12 is, of course, 8. So therefore, t equals 8. So we've solved it. However, I'll just show you a slightly different approach, which you may prefer, so I'm going to show it you just in case. Another way, using this information about the velocity being parallel to 3i minus 4j, what I could say now, using an alternative approach, when t equals t, the velocity is some k multiplied by 3i minus 4j, like I said here. So considering this is like a ratio of components, I can say the j component as a ratio to the I component must be minus 4 to every 3. I'm doing j over I in terms of thinking of it as y over x, like a gradient, a direction essentially. And so then, knowing that the velocity is in this direction, using the second equation for the velocity here, I can then say the same about these I and j components and say these must be in the same ratio as these two. So therefore, because vt is also this expression here, when t equals big T, that j component as a ratio or as a fraction of its I component must be 4 minus 3t over 2t minus 1. So then, if I equate these, I can essentially say here that all I'm doing is saying one fraction is equal to the other and then solving. I'm not going to solve it. You can do that yourself if you want to see if it works, but that's just how you'd do the alternative approach if you wanted to. Part B of this question, we need to find the distance AB, where AB is just the distance from the point where it started, time t equals 0, to the point B after time 4 seconds. So it's just basically how far has it travelled in 4 seconds, direct distance-wise. So because the acceleration is constant, as we can see here in this wording, we can actually use the 𝐶𝐒 formulae in vector form. So because we're interested in a distance here, distance displacement essentially, so we can use the adapted version of s equals ut plus a half at squared. And so if I do this in vector form, and also be careful to colour code a few things. So I'm going to say this is A, so I'm going to have A as this red vector, and u is the initial velocity when time is 0, and so this here is equal to u. So r is equal to u multiplied by t in terms of s equals ut plus half at squared. So that's ut then plus a half multiplied by a multiplied by t squared. So when time is 0 rather, the components would become 0 because vector u, which is minus I plus 4j multiplied by 0, would just all become 0. But I'll just write it in anyway, just for the sake of it, because why not? So u0 then plus a half multiplied by a multiplied by 0 squared. In other words, that just equals 0i plus 0j. Oops, wrong colour. So r0 is just 0i plus 0j. So in terms of a coordinate grid, we can imagine it starting from A, and that this is essentially the origin. whereas when the time is at 4 seconds, r, when time equals 4, is going to be u times 4, then plus a half vector a multiplied by 4 squared. So 4 lots of u is going to be minus 4i, and 4j would become 16j. And then this here, a half times 4 squared is 8. So essentially we're going to multiply the acceleration vector by 8. The a vector is this, so multiplying all components by 8, 2i becomes 16i, and minus 3j becomes minus 24j. Now we can simplify this down in terms of just simply I and j components. So in terms of the I components, I've got 16i here, take away 4i, so it'll be 12i overall, and then 16j minus 24j, that gives minus 8j. So in terms of picturing the position vector at time equal to 4 seconds compared to the origin, we can picture this here, like so. So this is A, and this is B. So A and B. So therefore, picturing the distance between, that's the magnitude of AB. And we can just use Pythagoras for this. So from A to B, going in the I direction, is a distance of 12. And from A to B in the J direction, we're going down 8 because we have minus 8j. And so the magnitude of AB, which in geometric terms is the distance AB, will simply be 8 squared plus 12 squared. So 12 squared plus 8 squared, then all square rooted. So therefore, AB will be the square root of 12 squared plus 8 squared. You could put minus 8 in brackets all squared if you really wanted to, but you really don't need to. So if you want to, you can calculate this, or you might notice something about these actual values before you do. I'll explain what you may have noticed after the fact. 12 squared plus 8 squared, that gives 4 root 13. So put this in like so. I was going to spot here that 8 and 12 are both multiples of 4, so it's not actually a coincidence that we get a 4 on the outside here, but have a bit of an explore about that. Anyway, the exact distance AB is 4 root 13. And of course include the units, so it's 4 root 13 meters. And if you wanted to, you could convert this into a decimal, but exact form is absolutely fine. Question 3 now. So here we've got two blocks, A and B, of masses 2m and 3m respectively, attached to the ends of a light string. So this here is the string. Initially A is held at rest on a fixed rough plane. The plane is inclined at angle alpha to the horizontal ground, alpha's here, where tan alpha is 5/12. We're going to return to this fact in a moment. The string passes over a smooth pulley P here, and the part of the string from A to P is parallel to a line of greater slope of a plane. So this just means the string here is parallel to the slope. Block B hangs freely below P, like so, and this is figure 1. I've just not labelled it as such. The coefficient of friction between A and the plane is 2/3. In other words, this plane is rough, so friction is going to be involved. The blocks are released from rest with string taut, and block A moves up the plane. The tension of the string immediately after the blocks are released is capital T, and the blocks are modelled as particles, and the string is modelled as being inextensible. Question part A, let's show that capital T is 12 mg all over 5. So quite intimidating, to be honest. 8 marks and just a load of information chucked at us. So what does capital T mean? It means tension. So we need to consider the tension initially. So the tension is going to be acting along the string. So relative to A, the tension always acts away from an object, of course. Need to remember that. So the tension at A will be acting away from it. So we can draw a red line, call it capital T, acting along this string from A, and the tension will be acting at B as well, but this time we'll be acting vertically up at B. So labelling of the tensions at A and B, we have the following. And then what we need to do, building up the diagram step by step, is to consider other forces acting on A and B. There's always going to be a force due to gravity, also called the weight. So if A has mass 2m, its weight will be 2mg, and if B has mass 3m, its weight will be 3mg. So let's add on the weights. Now I'm just returning to this angle alpha for a second, which I'm going to highlight in yellow. Now this angle alpha also can make an appearance here. If we can construct a right-angled triangle with an hypotenuse of 2mg, and imagine a line perpendicular to the slope coming out from 2m down here, and another line going parallel to the slope, like so, then here, perpendicular and parallel makes a right-angled triangle. And this angle here, in between the vertical and the line perpendicular to the slope, will also be alpha. So I can construct a right-angled triangle including alpha here, like so. And this is now our setup for resolving the weight here into components parallel to the slope and perpendicular to the slope. And so doing that, the component opposite to alpha, this one here, will be 2mg sine alpha. This component will become 2mg cos alpha. And because we then can resolve, we can replace 2mg with its components like so. Just 2mg sine and 2mg cos. But we can go one further and actually think about what sine alpha and cos alpha is, based off this information here, where it talks about tan alpha being 5/12. Well, if tan alpha is 5/12, we can imagine a right-angled triangle where that's the case. Tan is the opposite divided by the adjacent, so we can now sketch out a right-angled triangle with an opposite side of length 5 and an adjacent of 12, and the angle will be alpha, like so. So, based off this little sketch now, I can now think about what the hypotenuse of this triangle would be, just by applying some basic Pythagoras. So the hypotenuse here will be 12 squared plus 5 squared, and then all square rooted. So the hypotenuse here would be 13. And then, remembering the trig ratios sine and cos, sine alpha will be 5/13, and cosine alpha will be 12/13, like so. Now, because we know what sine alpha and cosine alpha are as exact fractions, we can neaten this up here in terms of the 2mg weight being resolved. So if sine alpha is 5/13, 2 times sine alpha is 10/13, and so this component here becomes 10/13 mg. So just getting that a bit neater, we can call that 10/13 mg. And this one here, 2 cosine alpha, will be 2 times 12/13, which is 24/13. So this simplifies to 24/13 mg. So now we've got those simplified, we now need to think about other forces acting on A. We can't forget that there's a coefficient of friction in between A and the plane. So the coefficient of friction is 2/3. It also says that the blocks are released from rest with the string taut and A moves up the plane. And so if there's friction and A is moving up the plane, if it's in motion, then the friction will take on its absolute maximum value. So in other words, the friction will be at its maximum, which will be the coefficient of friction multiplied by R. So we can add this on here, F max 2/3 multiplied by R, and it will always be acting opposite to the motion. Friction always acts to resist motion. So because we're told in the question A is moving up the slope, the friction in this case will be acting down the slope like so. This also reminds us about R. R is the normal reaction. So another force acting on A, which we need to consider, is the reaction going from this block here, going perpendicularly outwards from the slope. So 2m will have a force acting upon it from the slope itself, going in this direction, and that will be R. So let's add on R, like so. Now we can start to actually consider forces acting on A. So all our force diagrams now complete and nicely resolved. So just consider forces on A going perpendicularly to the slope. So perpendicular to the slope, the forces will balance. The only acceleration is up the slope. There's no acceleration this way. And so the forces perpendicular to the slope going up must be equal and opposite to the forces perpendicular to the slope angled down. So in other words, R must equal 24/13 mg. So therefore, we can actually simplify this expression for F max. So F max is 2/3 multiplied by this here. So 2/3 times 24/13, we can neaten this fraction up. So 2/3 times 24/13. Well, basically, you can just think about what's 2/3 of 24. That's just going to become 16/13. And so we can neaten this up. So F max is 2/3 of R, which is going to be 16/13 mg. That's the force going down, the force due to friction. So now we consider forces on A, but this time going parallel to the slope. So the object A is accelerating up the slope in this direction T, and so T will be the prevailing force. And so the net force going up will be T minus the forces going in the opposite direction to T. So the net force going up will be T minus F max minus this component of the weight going down the slope. So that'll be the overall force going down, and according to Newton's second law, that'll be the mass of A, 2m, multiplied by its acceleration. So piecing that together, the overall force acting on A, going up the slope, which is this expression here, is equal to the mass of A, 2m, multiplied by the acceleration. Now looking here about these mg parts, if I take away 16/13 and take away another 10/13, that's minus 26/13. That nicely neatens up to 2 mgs. So I can simplify this slightly now with T minus 2 mg equals 2 ma. So it just looks much nicer for the next part. Now thinking about forces on B now, but this time forces on B going in the vertical direction, the prevailing force will be in the down direction because B is going downwards, and so the overall force going down will be 3 mg minus T. So applying Newton's second to that, the overall force, 3 mg minus T, the resultant equals a mass of B, 3m, multiplied by the acceleration. And what do you know? We have simultaneous equations. So what we can do here, we can eliminate T, we can actually add to work out what the acceleration is. Then from there, we can work out T as required. So if we were to add these two equations together, so T plus minus T will cancel, 3 mg plus negative 2 mg just gives us 1 mg, and 2 MAs plus 3 MAs gives 5 MA. Dividing through by 5 and cancelling the m, we can therefore see that the acceleration must be 1/5 g. So now I know that the acceleration is 1/5 of g, I can highlight that and then plug this in to this top equation. To be honest, I could choose either equation, but I'm going to choose to plug in 1/5 g for A here instead. So if I just highlight and box off this equation here, and then plug in what I know, I'm now going to get that T minus 2 mg will now be 2 times 1/5 g times m. In other words, this side here is going to become 2/5 mg. So this here, once substituting in that A is 1/5 g, becomes this. So now I can work out what T is by simply adding 2 mg to both sides. So if I do that next, therefore the tension is 2/5 mg plus 2 mg. So if I factorise out the mg, the coefficient in front of the mg is just going to be 2/5 plus 2. So not that you really need to do this step, but if you want to convince yourself, 2/5 plus 2, that will give 12/5 as required. So therefore T, which is 2/5 mg plus 2 mg, simplifies to 12/5 mg, or 12 mg over 5 as required. So that's part A completed. Now let's think about question B, or part B. So if we just take A away for a second and introduce part B, which is this here, it says that after B reaches the ground, A continues to move up the plane until it comes to rest before reaching P. To determine whether A will remain at rest, carefully justifying your answer. So what will happen here, if B hits the ground, there'll be no tension supporting it. B will be supported entirely by the normal reaction from the ground, and then this bit of a rope, or string I should say, will become slack. So what I'm going to do here is just try to alter slightly this diagram so you get an idea of what's going on. And so essentially B will have hit the ground, so I'm going to erase B here and just sketch over what it'll look like. So B instead will be on the ground now, like so, and this string will be slack, so no tension. In the same way, the tension will disappear from A as well, so I can get rid of this tension force there. There'll still be a reaction force, of course, because it'll still have its weight, but now the only thing will be the force going down due to the component of the weight, 1013 mg. Once it comes to rest, this force component of the weight will be acting down the slope, so what will happen now is this friction will actually switch sides. The friction will always try to resist motion, you see, so the motion would tend to go down the slope once this tension vanishes, so the friction will actually work against 10/3 mg. So going back up the slope will be the friction, so just change its direction here, only this time it won't necessarily be F max, I'm just going to call it F. So over here, just remind ourselves that F max is 16/13 mg, then clearly 16/13 mg is bigger than 10/13 mg. So the resisting force for friction would have to be 10/13 mg to keep this in equilibrium, in other words, to make sure it doesn't go down the slope. So A will remain at rest. It's not going to slip down the slope because F will assume the value of 10/3 mg. 10/13 mg rather. So essentially A will remain at rest. And all we need to say here essentially, because the limiting friction, F max, which is 16/13 mg, that's greater than the component of the weight going down the slope. So the friction is able to resist the force. Finally now for question 3, part C. So say goodbye to part B, introduce part C. So for part C, we need to suggest 2 refinements to the model that would make it more realistic. Here I'm just going to suggest you keep your refinements simple, don't make them overly articulate, and just keep them relevant and to the point, and you can't go too far wrong. So any 2 refinements. So in any order, I'm going to give you 4 suggestions. There could be more than 4. So any 2 of the following. So the first one that I think you could suggest is you could model the string as extensible. Actually, a string will be extensible, even to a small degree. So if you're ambitious, that could be thrown into the model as well. Alternatively, you could model the string as having a mass. It certainly will have a mass, and that will affect the system, even if ever so slightly. The third refinement could be to consider the friction at P. Although this is going to be modelled as frictionless, nothing's ever 100% frictionless really, especially not with a pulley, so that could be factored in as well if you wanted to improve it. And another one I'd suggest, you could consider the air resistance on A and B. As B's moving down and A's moving up the plane, there will be a tiny bit of air resistance no matter how small. You could also mention that A and B aren't point particles. You could consider their dimensions, so that could even be a 5th one to mention. But that should suffice. Any 2 of those 4, or the 5th one, if you want to think about them not being point particles. In question 4, we have a ramp AB, which has a length 8 meters and mass 20 kilograms. So we're told it's resting in equilibrium with the end A on rough horizontal ground. So this is a clue. There's going to be some friction at A. The ramp rests on a smooth, solid cylindrical drum, which is partly under the ground. So it's semicircular above the ground and semicircular below. And the drum is fixed with its axis at the same horizontal level as A. So all that's saying is we can consider this as like a 2D problem. The point of contact between the ramp and the drum is C, where from A to C is 5 meters. This is figure 2, but I've just not labelled it as such. The ramp is resting in a vertical plane which is perpendicular to the axis of the drum at an angle theta to the horizontal, where tan theta is 7/24. It's modelled as a uniform rod. That's always a relief, because that means we can take the centre of mass to be at the centre of its length, the middle. However, for part A, all we need to do is to explain why the reaction force from the drum on the ramp at point C acts in a direction which is perpendicular to the ramp. So if you notice, it's not saying the normal reaction force, but just the general reaction force. So the reaction is a combination of the normal reaction plus any frictional force which may be occurring. So in terms of this, when it's saying the reaction from the drum, it just means this sort of force here acting perpendicularly up from C. And we're told it acts perpendicularly, and we just need to think why. Well, we were told earlier that the drum is smooth, so therefore there's going to be no friction acting upon the rod at point C. So because there's no friction, the only force acting on this ramp upon C is just the normal reaction force. So therefore, the only thing acting on it is the normal reaction force, which by definition is perpendicular to the surface. So then we can just say, because the drum is smooth, the only reaction from the drum on the ramp is just going to be the normal reaction force. I've called this R. Now for part B, what we need to consider now for part B, it's a big 9 marker. We need to find the magnitude of the resultant force acting on the ramp at A. So I'm going to label this one here RC actually, and then the reaction at A, we're not entirely sure. This is what we needed to work out. Well, one thing we can say that's going to happen at A is there's going to be a normal reaction. So I'm going to just draw a line going up like so in blue, and I'll call this N for normal reaction at A. As well, we're told that this is a uniform rod, so therefore centre of mass is going to be COM, centre of mass, will be 4 meters from A. Because 8 meters, so half of 8 is 4. So from a point which is 4 meters along, which roughly is going to be, say, here, I'm going to draw a line down which is going to denote the weight of this. So of course, if the mass is 20 kilograms, then its weight will be 20 g. So going downwards, we've got a force of 20 g. In fact, I'll move that 20 g to the other side, like so. So what we need to consider now as well is forces in certain directions. So what else do we need to label on? Well, we're told as well that this ground here is actually rough. So it's rough horizontal ground. This implies that there's going to be friction, of course. So the friction will always act against the tendency for motion. So the friction this way, if this were to slip, this ramp would slip to the left, it'd fall downwards. So the friction, if anywhere, will be acting to the right. So the friction force, we can add on, I'll do this in a purple line, that's going to be acting this way from A, and I'm going to call this just F for friction. So, 9 marks, where to begin? Well, what we could consider here, because we're told masses, we could resolve forces going vertically. So first of all, let's just consider forces going up and down. So forces acting up, because it's in equilibrium, will equal forces acting downwards. And so the forces acting up, we've got N, plus as well we'll have a component of this reaction at C, which will be going up as well. So this here, we can resolve into components going vertically and horizontally. So if we just do that now, a vertical component and a horizontal component like so. Because this is theta, this angle here will also be equal to theta as well. So the RC, we can now resolve into horizontal and vertical components. And so the component which is going vertically up will be RC cos theta, and the component acting to the left, this one will be RC sine theta. So in fact, I'll leave that as RC, and I'll label this as the original RC. So this is the resolved components, and RC is the hypotenuse. So as you can see, the component of R going vertically up is RC cos theta. So N plus RC cos theta going upwards must equal the forces acting downwards. The only force acting down is, of course, the weight of the ramp itself. So that will equal 20g. We could also consider, in the same way, forces going left and right. So just going horizontally across. In terms of thinking of just forces purely going horizontally, there's a frictional force acting at A to the right on the ramp. So that force acting to the right, which is F, which is the only force acting to the right upon the ramp, must be equal and opposite to all the forces acting to the left. And acting to the left, we can see here it's just RC sine theta. And sine and cos theta and all this, we can actually do one better because we're told what tan theta is. We're told tan theta is 7/24. So if we construct a right-angled triangle for that, we can then work out the exact ratios sine and cosine. So if this one here is theta, then the tangent's defined as opposite divided by adjacent. So 7 I can put there, 24 here. Label that theta. Therefore, the hypotenuse will be 7 squared plus 24 squared, all square rooted. So if we just do this on the calculator, square root of 7 squared plus 24 squared, you'll see it's a Pythagorean triple, gives us exactly 25. So based on this piece of information, we can then nicely say that sine theta is opposite over hypotenuse, so sine will be 7/25, and cos theta is going to be 24/25. So we can input these in a moment. In fact, why not treat ourselves? Why not just do it now? So this one here, because I know that cos theta is 24/25, I can then just say that n plus 24/25 lots of RC equals 20g. So I'm just filling in that I know that cos theta is 24/25. Similarly for F, using that sine theta is 7/25, I can say that therefore force F will be 7/25 of RC. So far so good, but with these questions, often as well as considering forces in one direction or another, this may also be a question where we need to consider moments. So now what we can consider is moments going about a certain point. It's always quite a tactically astute choice to take moments about a place, which will eliminate the necessity to know as many forces as possible. So at A, we don't know 2 forces, so if we were to take moments at A, the fact we don't know N and F wouldn't matter because N and F go immediately through point A. So these would have no turning force relative to moments about A. So now, coupling this with moments about A, then the clockwise moments will equal the anti-clockwise moments. So clockwise relative to A, there's only going to be one force, which is going to be this 20g. So 20g relative to A will be turning round like so. So that's going to be 20g. The force is 20g. To find the moment, we obviously multiply by the distance of that force from the point we're taking moments about. So from A to that line here, well, I know from A to 20g, that was a length of 4. Remember we said that the centre of mass will be half of 8, which is 4 meters from A. So if that's 4, then from A to this point here will be 4 multiplied by cosine theta. So 20g times 4 cosine theta. That's distance from there to there. That must be equal and opposite to the anticlockwise moments. The anticlockwise moment will come from r subscript c, and the distance of RC from A, the direct distance, is of course just 5. From this equation, we can actually work out what RC is. So therefore, we can say the reaction at C is going to be 20g times 8. So it's going to be 80g cos theta. Cos theta, of course, is 24/25, so I can fill that one in. All divided by 5. So let's see what that gives us. So if we use a calculator and just type this in carefully, move this away so we can see what we're actually doing. So 80g means 80 multiplied by 9.8. And then I'm going to add on, so I'm going to multiply rather, that by 24/25. I'm going to divide this whole thing by 5. That gives this awkward number here, which is 150.528. So reaction at C is 150.528. We can then work out from that the normal reaction, and indeed the friction. So therefore, the friction will be RC sine theta. So I know what reaction at C is now. So that's going to be 150.528 multiplied by sine theta, which of course we were told. Well, we're not told, we've worked it out. So sine theta is 7/25. So that times 7/25 So I've got the answer. So I should multiply it by 7/25. That gives me 42.14784. And finally, we can work out what n is. So from this, we had n plus 24/25 RC as 20g. So we can also work out n. So n is going to be 20g minus 24/25 of reaction at C, which we now know is 150.528. So plug this in, work out. So we're going to have 20g, which means 20 multiplied by 9.8, of course. Subtract 24/25 of 150.528. Whoops. Almost made a mistake there in terms of how I type this in. So again, always be careful. Goes for me too. We get here 51.49312. So now it's just a case of seeing how this all fits together. 49312. So the magnitude of the resultant force, so this resultant force acting on A, is going to be a combination of N and F. And so N plus F will give you the resultant force. So resultant is the net combination of the normal reaction force plus the friction. So if you imagine joining these two together, like so, if I just imagine moving F up here, then clearly the magnitude would be the line going straight from A to F. So in other words, what we can do here is use essentially Pythagoras to work out the magnitude. So if I just label this here the resultant, which I'm going to call RA, which is our target, we can then do the final step. So therefore, the reaction at A, the magnitude of it at least, will be the square root of this one squared, which is 51.49. I can squeeze this all in. 49312. So square root of 51.49312 all squared plus the square root of the other one squared. So f, the magnitude of f we worked out was 42.14784. So it's also that. And squared. So just type it in very, very carefully into your calculator. So if I move this over here, so 51.49312, I've already got n, so I'll keep this as my answer. So that one, answer squared, and then just add on this one, 42.14784 all squared. Press equals, and then round suitably, we'll get 66.5 newtons. And you can now breathe a sigh of relief. That was not a straightforward question. 9 markers seldom are. Finally, for question 4, we have part C of it. So part C, it says the ramp is still in equilibrium in the position shown in figure 2 here, but now the ramp is not now modelled as being uniform. So now we're given that the centre of mass of the ramp is assumed to be closer to A than to B. So actually we're not thinking this 20 G is bang in the middle. We're thinking it's actually a bit closer. So actually this distance here will be less than 4. So I don't know, maybe it's, let's go for just a number. Let's say it might be 3.5. Who knows? But let's just go for a number so I can explain it. So if it were a bit closer to A, how would that affect the answer to part B? So how would it affect the magnitude of a normal reaction between the ramp and the drum at C, rather? Well, the magnitude of a normal reaction between the ramp and the drum, we gave that the letter R subscript C. And if you look here, we've actually got this recipe for working out what RC actually is. So these are the numbers, the values that came into this equation here. But now, if you notice this 4, that 4 came from the idea that the distance of the centre of mass, the distance of the weight from A, the line of force, was 4 cosine theta. But now, this would be a smaller number, for example, 3.5. And so then, we're taking a smaller number here, because we're multiplying by something less than 4 times cos theta, and then dividing it all by 5. If this number's made less, RC will be less. So, to put it simply, the reaction at C will decrease. And here we are at the last question, question 5. So the points A and B are 50 meters apart on horizontal ground, like shown in figure 3 in the bottom right here. At time t equals 0, for 2 small balls, P and Q, are projected in the vertical plane containing AB. So this is just assumed to be all happening in a 2D setting. Ball P is projected from A with speed 20 meters per second at an angle of 30 degrees to the horizontal AB, whereas Q is projected from B with speed U, an angle theta to BA, as shown in figure 3 again, and at time t equals 2 seconds, P and Q collide. Until they collide, the balls are modelled as particles moving freely under gravity. So for part A of this, what we need to do is to find the velocity of P at the instant before it collides with Q. So what I'm going to suggest we do here is to resolve the motion of both P and Q into horizontal and vertical components. So if I just think about P here in, I'll call this, well, I won't call it, I'll say it's red. So if P is actually going up here, I can label this into its constituent components. So it's going to have a vertical component like so, and it's going to have a horizontal component this way as well. In a similar way for Q, if I just label Q with a blue arrow instead, Q again will have a vertical and horizontal component to it. So the component going vertically Let's add on like so, and horizontally for u as well. Now for p, we can easily resolve this. So the component of the velocity going in the horizontal direction will simply be 20 cos 30. But we need to know that cos 30 is root 3 over 2. So 20 multiplied by root 3 over 2, that would just give us 10 root 3 in this direction. Whereas in the vertical direction, the initial motion, when t is 0, it'll be 20 sine 30, which will just be 10 meters per second going up. For q, all we know is in terms of u and theta. So keeping it purely algebraic, the component of the speed going to the left, the magnitude of that will just be u cosine theta, and going up will be u sine of theta. But of course, for part A, we're just considering the velocity of p at the instant before it collides with q. One thing to note is it's falling under gravity, both of these two balls. It says here as well how it's modelled. So if we look here, it's moving freely under gravity. So there will be acceleration due to gravity in the vertical direction, but because no air resistance is being mentioned, the horizontal components of motion, the horizontal velocities will be constant because they're not going to suffer from any air resistance. So if I just think about p for a moment, so the component of the velocity going in the x direction will just be a constant 10 root 3. Whereas in the y direction, the velocity will have a component as well. Whereas this one here, we need to think in a bit more depth because this will have a acceleration in this direction. So let's just think about this in terms of suvat. And I'll take the up direction to be positive because it's going in an up direction to begin with. So the acceleration is going to be minus 9.8. In other words, it's going to be the gravity acting opposite to what I've defined to be the positive direction. The initial speed going upwards, of course, is 10. I want to find out the final speed, so I do want to know v. So I'm going to just put that I do want to know v, put a question mark there. And as well, I know that at time 2 seconds is going to be the time after it's just about to collide with q. So the time is going to be 2 seconds. I know it says the velocity of p at the instant before it collides with q. So think of it as 2 minus a trillionth of a second if you really want to. So 2 seconds, it still stays as 2 seconds. S, I don't know, I don't care. So considering the velocity of y, I need an equation of motion which doesn't involve s. So here I can just use v equals u plus at. So in other words, vy will be u of y, which will be 10 plus at, acceleration in the y direction, times t. So velocity of y will be 10 plus the acceleration, which is minus 9.8, because it's in the opposite direction, multiplied by 2. And that will give you minus 9.6. So therefore vy, the component of the velocity in the vertical direction, is minus 9.6. So if I just piece these together for particle p, we can now imagine the motion, the direction of its velocity. So it's going to have a component going this way, horizontally, that's going to be 10 root 3. And as well as that, the horizontal component, so the vertical component is minus 9.6. Because it's a minus, it means it's going down, essentially. So that's going to be 10 root 3. That's going to be minus 9 root 6. The velocity, the magnitude of the velocity is going to be the size of this hypotenuse here. So for part A, I can say the velocity of p is going to be the square root of 10 root 3 all squared, just using Pythagoras, plus minus 9.6 all squared, and all that square rooted. So if we just do this now, we're going to get square root of 10 root 3 all that squared, plus brackets. You don't need to put a minus, of course, but just to keep it in terms of exactly how I've written it down, I get 19.8. So to three different figures, I've got 19.8 meters per second. However, because it's saying to find the velocity, we also really need to find its direction too. This is the speed. Velocity is a vector, so I need to find the direction. So I can find here this angle. So its velocity is 19.8 meters per second, and it's at an angle of theta. That's going to be 10 minus 1. If I just think of this about the just pure size of the side, that's going to be 9.6 over 10 root 3. So bash this into the calculator, shift 10 minus 1, 9.6 over 10 root 3. Whoops, done the bracket there, I want it there instead. So I get there 28.99, essentially 29 degrees. So it's an angle of theta, which is 29 degrees below the horizontal. So I've given the magnitude of the velocity, and as well I've given the angle. So therefore I've satisfied everything I need to answer part A fully. Part B, I now need to find for part 1 the size of the angle theta, and also part 2 the value of u. Again, this is a 6 marker. So I'm not really going to aim to do theta or u, I'm just going to see what drops out if I try to piece together the information. So let's just think about the information we've been given so far. Well, we're told at time t equals 2 seconds, P and Q collide. So that's definitely worth noting, as is the fact that they're 50 meters apart on horizontal ground. So what this is saying is, after 2 seconds, if they've collided, basically A and the distance, P has travelled this horizontal distance, and Q will have travelled this horizontal distance. So the total of the distances they must have travelled must be 50. But of course, in terms of horizontal distances, the horizontal components of their velocities are going to be constant. And so basically we can use simply for motion with no acceleration that the distance travelled will simply be the velocity multiplied by the time, which in this case will simply be velocity times 2, because we're talking 2 seconds. So we can get an equation from this. So considering P, the distance that will travel in 2 seconds will be 10 root 3 times 2, which will be 20 root 3. Then if I consider how far Q would have travelled, its horizontal component of speed is u cosine theta, so that multiplied by 2, because it's 2 seconds, that's going to be 2u cosine theta. So that distance plus this distance needs to give 50. That's the distance that P covers, this is distance that Q covers. And that's just thinking about distance going left and right. Now, we can also consider something else as well, though. And that's also the vertical motion. So vertically, they're going to collide after 2 seconds, which is basically saying that after 2 seconds, they need to be at the same heights if they've collided. So this one here, if I use s equals ut plus a half at squared for this next part, they need to be at the same height. So in terms of P, what I can say is the vertical height that P will be its initial vertical speed multiplied by t, so that's going to be 10 times 2, so 10 times 2 multiplied by half times a times t squared. Now the acceleration, because it's acting opposite, it's going down, it'll be minus 9.8. So half of minus 9.8 is minus 4.9, and t is 2, so that's minus 4.9 times 2 squared. So that's the horizontal displacement of p after this time period. That must equal the same vertical distance that q is after 2 seconds. So for q, its initial velocity going upwards is u sine theta, and so u times t will be 2u sine theta. Again, minus half times a, so minus 4.9 times 2 squared once again. So from this equation now, we can hopefully see we can just add minus 4.9, add 4.9 times 2 squared to both sides. Essentially, we can cancel this bit and that bit. So essentially, considering the vertical motion, 20 equals 2u sine theta. So from that, I can say that u sine theta equals 2. So u sine theta equals 10, just dividing both sides by 2. And from this one here at the top, I can also isolate u cos theta. So if I divide everything by 2, that'll become 25. And of course, minus this to the other side. So minus 20 root 3, but again, I need to half that as well. So that becomes minus 10 root 3. So what I've got now is two simultaneous equations, which I can now solve. So from the top one, I've derived this formula for u cos theta. And from the vertical motion considerations, starting from here, I then derived this. And so taking these two here and solving simultaneously, we'll be able to get expressions for both u and theta. So if I call the top equation, for example, call this A, the bottom equation, call this B, it doesn't really matter what I call them. If I do A divided by B, that'll then give me u sine theta divided by u cosine theta. That'll then give me tan theta. So tan theta is going to equal 10, all divided by 25 minus 10 root 3. So therefore theta will be tan minus 1 of all of that, of 10 over 25 minus 10 root 3. So if we just do this on the ClassWiz or any other suitable calculator, so shift tan minus 1, 10 over 25 minus 10 root 3, close brackets, press equals, we get that theta is 52.5 degrees. So for 1, theta is 52.5 degrees. For part 2, we want the value of u. So what I did with a and b, I did a divided by b, whereas what I could have done instead, if I were to take a and b and then did a squared plus b squared, the whole of equation a squared and all of equation b, square it, then add together, what I'm now going to do, I'll just clear myself a bit of space over here, whoops. This one here will become u squared sine squared theta, plus underneath u squared cos squared theta. That'll equal 10 squared, which is, let's leave it as 10 squared actually, plus the bottom one squared, 25 minus 10 root 3, all squared. Now if I factorise out u squared here, I'll get sine squared plus cos squared, which of course is just 1. So then that just becomes u squared on the left hand side over here I can neaten this up. So what is 10 squared plus 25 minus 10 root 3 all squared? Well, let's see. So 10 squared plus 25 minus 10 root 3 brackets all squared. That gives me 158.974, blah, blah, blah. So then, therefore, for part 2, u will be the square root of that. So square root of the answer and round to an appropriate degree. 12.6. So u is 12.6 meters per second. And for part 1, theta was 52.5, of course. Now there's a bit more, just part C now. For part C, we need to state one limitation of a model other than air resistance that could affect the accuracy of our answers we've just received. So a few different pointers. One thing we could say is that balls aren't actually particles. They're considered to be point particles for not going to be that in this case. Sort of an extension of that point, very similar. You could have also said maybe the dimensions of the balls haven't been considered. They're not going to be point particles, so that's a limitation of the model too. So these 2 points are very closely related. Something else you could have maybe said, the balls might have spin. So although it's considered that the point particles, they still could have spin and other twisting forces and things going on, which could affect the actual outcome and the accuracy of our answers. As well as that, we could have simply said something like this. The last one's probably my favourite one that I'd go for personally. We're assuming in the model that the motion's purely 2D. I know it mentions air resistance, you can't really say that, but there might be wind blowing them off course. So wind is a bit different to air resistance, but no motion involving something moving through air is ever going to be purely 2D. It's going to blow back and forth even to a slight amount. So one of these 4 points would suffice. So that wraps up the paper. We've got to the end, so it just remains for me to say sincerely a big thank you for watching, and it is sincerely appreciated. If this hasn't made sense at any points, do let me know, leave a comment for any feedback, either positive or negative, but be gentle. And let me know, of course, if you need any help, if you see me around school. So keep plugging away, never give up, and I'll see you next time in the next video.